Well, let's take a look at another exam. Math 265, also called multivariable calculus. Good stuff. We're going to be getting into applications of derivatives, maybe some optimization. Lots of fun ahead. So let's get ready to get going. And of course, the thing we need to do to get ready is to put our name. If we don't put our name, we're not going to get the credit. So here we go, solutions. And we're off. Number 1, we're asked to find all unit direction vectors, u, and the little arrow on top tells us, yeah, it's a vector, in which the directional derivative of the function y(e) to the minus xy at the point 0, 2 has the value 1. All right, so there's a couple of key things, but of course, the most obvious key thing is we see this word directional derivative. All right. And okay, so there's a few other things. We have the function, we have our point. So we say, all right, how do we take a directional derivative? So oftentimes this is denoted d sub u of f at p. So d for derivative, u is the vector, in this case, that kind of u there. F is our function, and p is our point. Well, that's the gradient of our function at our point dot u. All right, so there we go. That's what we're after. Okay, so probably a good place for us to start is finding that gradient, since that's going to play a role in our answer. So if our function f of xy is y(e) to the minus xy, then the gradient of our function, well, that's our partial derivatives, and it's a vector of the partial derivatives. So we say, okay, take the derivative with respect to x. So the y's are treated like constants. There's only one x, and when we take the derivative, well, this minus y comes down. So we get minus y squared, right? Minus y times y, e to the minus xy. And then for partial f, partial y, all right, this is partial f, partial x, product rule, because there's two y's. Derivative of the first, e to the minus xy times the second, and then the first, y, times the derivative of the second. Well, now the y's are a constant, the y's are the variables, minus x, that's a constant. So that comes down, so we get minus xy e minus xy. All right, so there's our partial f, partial y. All right, now we continue. What do? Well, we're going to plug in our point. Our point is 0, 2. So here is our p. So the gradient of f at p is, well, anywhere where you see x, we have 0. Great, awesome. So you're going to get e to the 0, which is 1, e to the 0, which is 1, 0 is 0. So what's going to be left? Well, we have the minus y squared, so that's minus 4 times e to the 0, which is 1, comma, e to the 0, which is 1, subtract 0 times 2 times e to the 0 is 0. Or if you like, that's minus 4, comma, 1. Okay. Now, we've done some work. We've found this part. What do we need? Well, we need u. Well, that's actually what we're looking for. All unit vectors so that the directional derivative has the value 1. So we say, oh, okay. Well, that says what's going on here. We want our gradient of f at p dot u needs to equal 1. And u has to be unit. Okay, so we'll think of u as our vector a comma b, and we'll note that a squared plus b squared equals 1. Now this part right here is just another way of saying it's a unit vector. So if you square up the entries and add, you get 1. It's the magnitude. Okay, so we need minus 4 comma 1 dot a comma b equals 1. So that says, well, we need minus 4a plus b equals 1. All right, now what do you have here? You have two equations, minus 4a plus b equals 1, and a squared plus b squared equals 1. Two equations, two unknowns. All right, well, we need to solve. Now, the nice thing here is in this first equation, there's a single b. So we say, all right, let's solve for b there. So we could say that b is 1 plus 4a. And now that we know what b is, we can say, well, let's come into here. So we get a squared plus 1 plus 4a squared equals 1. All right? How you doing? Okay. Just remember, what's our goal? Our goal is to find our a and b. So we're working through, and we're getting close. We're now down to one function for one variable. That's the ideal. Well, if we square, a squared plus here, squaring this will be 1 plus 4a plus another 4a. So it's 8a plus 16a squared. And that equals 1. Well, there's a 1 on both sides. Nice. Cancel out. And we can also group things together. Okay, so we have 17a squared plus 8a equals 0. Which tells us, since we can factor an a out, a times 17a plus 8 equals 0. Which gets us to two possibilities. All right, what's our two possibilities? Well, one possibility is that this first part equals 0, which is a equals 0. The second possibility is that this part equals 0. Well, okay, that's a little bit more unusual, but we would subtract the 8 divided by 17, negative 8 over 17. All right, now how do we get our b? Well, we know b is 1 plus 4a. Ah, well, perfect. That just means we plug it in, and then life is wonderful. Well, okay, so let's finish it up. Okay, so when a equals 0, b equals 1 plus 4 times 0, which is 1. And so that leads us to the vector 0, comma 1. All right. And then when a is equal to minus 8 over 17, well, b is equal to 1 plus 4 times negative 8 over 17. Well, let's be careful here. They have 17 downstairs, so we get 17 over 17 from the first term minus 32 over 17, right? 4 times 8. Well, 17 subtract 32 makes negative 15 over 17. And so our other vector would be minus 8 over 17, comma, negative 15 over 17. And so there are two vectors at work. And there we go. All right, great. So it worked out. Now, of course, you might say, oh, it looks kind of intimidating, but let's just remember the key is we have directional derivatives. We know how to take a directional derivative. There's going to be a directional derivative on this test. So we're just going to be prepared. We find our gradient at our point, and now it's just a matter of saying, well, we know we want a vector, and it has to be a unit vector. The directional derivative gives us our equations, two unknowns, and solve. And then we're great. Life is good. And we're off to a good start. Let's keep going. Number 2. For f of xy is e to the x times the natural log of 2y minus 1, find the second order Taylor polynomial at the point 0, 1. Okay. Now, this is not bad, but what's going to go on here is we're going to do lots of partial derivatives. So this is a test of partial derivatives, almost a test of stamina, if you will. Let's talk about what is the second order Taylor polynomial. And that's probably the key. If we know what that is, we're going to be good. Now, in general, if we talk about the second order Taylor polynomial at, I'll say, a point A comma B, well, we have some layers. The first layer says, well, if you only had a 0th order, you approximate it by the function, so f of AB. The next layer, which would be the first order, the partial derivatives come into play. So f of x AB times x minus a, and f sub y AB times y minus b. Now notice these are numbers you evaluate, not functions. All right, that's the first order. To get to second order, we're going to get to our second derivatives. So we're going to have fxx at AB times x minus a squared over 2. That's important. You need the 2. Plus fxy AB times x minus a y minus b. There's no over 2 here. Plus fyy AB. Whoops, I'm almost going to run out of space. Y minus b squared over 2. All right, so again, over 2. Now, why do we have over 2's here, not there? Well, think about taking two derivatives. Here, the 2 comes down, so you need to compensate. Here, there's no 2 coming down. It's always a 1 and a 1. All right, so what do we have to do? Well, we just have to fill in the blanks. So that's why this is a lots and lots of partial derivatives. And so let's take lots and lots of partial derivatives. There's really no other way to proceed with this kind of problem. Well, there kind of is, but that's a different story. Okay, so here we go. We will start with just our function. And we have e to the x natural log 2y minus 1. Our derivative with respect to x, well, the good news is there's only one place where x shows up, and that's easy to take. The derivative of e to the x is e to the x. All right, how about f sub y? xy. Well, now that you have the natural log. So that's where the y is. I should point up to here. You say, okay, derivative of natural log 1 over the inside times the root of the inside. So it'll be e to the x times 2 over 2y minus 1. So 1 over the inside, that's why the 2y minus 1 downstairs. The derivative of 2y minus 1 is 2. All right, now to the second derivatives. fxx, x comma y. All right, well, take the derivative of f sub x with respect to x. We get, well, derivative of e to the x is e to the x. Okay, great. Cool. Well, that's really very convenient. Okay, how about fxy? xy. Well, what would that be? Well, okay, come to f sub x, take derivative with respect to y, and it's again, as we talked about, 1 over the inside times root of the inside. So e to the x times 2 over 2y minus 1. And that leaves us with fyy, x comma y. Okay, so for this one, what happens? Well, you should think of this as 2y minus 1 to the minus 1 power. So let's do a little bit of work down here. We're going to move our page, give ourselves some space. Okay, so we're trying to take, here we go, this derivative. So I'm going to think of f sub y for a moment as 2e to the x, 2y minus 1 to the minus 1 power. So now when we take the derivative with respect to y, e to the x is still a constant. So what will happen is we'll get fyy. We have the 2e to the x. The minus 1 comes down. 2y minus 1 to the minus 2. And then times by the derivative of the inside. So what do we have when we put it all together? Well, we're going to get a minus 4 e to the x. That's upstairs. Downstairs, 2y minus 1 squared. Downstairs because of the minus. Whoops, 2y minus 1 squared. There we go. All right, pull it back down. Now, you may have noticed I put some gaps. That was deliberate because what we want to do is evaluate. So we're going to plug in 0, 1. So f of 0, 1. Wherever you see an x, put a 0. Wherever we see a y, put a 1. E to the 0, 1. Log of 2 minus 1, that's log of 1, 0. Log of 1 is 0, so that's 0. In fact, anywhere where we see a log of 2y minus 1, we're going to have things happen like that. So here, fx at 0, 1. E to the 0, log of 1, 0. How about fy at 0, 1? Well, we'll get e to the 0, which is 1, times 2, 2. And then 2 times 1 minus 1 is 1. So we get a 2. All right, how about fxx at 0, 1? E to the 0 is 1. Log of 1 is 0. So we get 0. Great. Well, this is going to help a lot. The more terms that we have that are 0, the easier the expression will be. All right, so here we'll have e to the 0, 1 times 2 over 1. So 2. And finally, fyy at 0, 1. Well, minus 4 e to the 0, that's minus 4. Downstairs we have 2 times 1 minus 1 is 1. 1 squared is 1. So minus 4. All right. So now we come in and fill in the pieces. Now, our f of 0, 1 is going to go away because it's 0. fx 0, 1 is 0. fxx of 0, 1 is 0. So that's good. Now to the non-zero pieces. Well, fy of 0, 1 is 2. Then we're going to times it by y minus 1. So 2 times y minus 1. And then fxy, that's 2. So we have plus 2. X minus 0. Whoops, I did not put 0, 1 here. Sorry about that. X minus 0 is x. And y minus b, that's 1. And then our last piece here, fyy, well, that's a minus 4. We also have a 2, so that's minus 2. And then y minus the y coordinate 1 squared. And that's it. That's our second order Taylor polynomial because we happen to be nice and several terms crossed out. Do you want to expand? No. There's actually strong reasons not to expand. Oftentimes what we can do is we can take our second order Taylor polynomial and use it to get nice approximations nearby, and in that case we really do want to keep things as they are. So this is a beautiful way to write our answer, and it's a nice answer. Number 3. Find and classify the critical points of the following function. X cubed minus y squared plus xy minus a half x. All right, so there's 2 stages, find and classify. So let's start with the find. So how do we go about finding? Well, for finding, we're looking for when does fx equal 0 and when does fy equal 0. So we're setting up a system of 2 equations, 2 unknowns, x and y. Of course, it's not just simple equations and simple unknowns. We're going to have some fun algebra, I suspect. All right, so what does this become? Well, take the derivative with respect to x. We'll have 3x squared. then the derivative of y squared is 0. Because right now we're taking the derivative with respect to x. Derivative of x times y, y. Derivative of minus a half x, minus a half. And we set that equal to 0. Now fy equals 0. Okay, derivative of x cubed, 0. Then derivative of y squared, minus 2y. Derivative of x times y is plus x. And derivative of minus a half x is 0. So we get equals 0. All right. So, well, this is good. We now know that minus 2y plus x equals 0. So we can say things like, for instance, x equals 2y. Or we could also say y equals a half x. And we can use that to plug in. Now it doesn't really matter which one we plug in, but since I have an x squared, let's go ahead and replace the y. We'll get to a quadratic. So what do we have? 3x squared plus 1/2 x minus 1/2 is equal to 0. All right, if we multiply through by 2, that would say 6x squared plus x minus 1 equals 0. All right, now can we factor? Maybe, it wouldn't, maybe, okay, let's try this. What would it have to be? Well, we have to break up the 6x squared, so it could be x and 6x, or it could be 3x and 2x. Given that we're shooting for an x here, let's go with the 3x and the 2x. Let's try this out. And what do we need? Well, 1, not a lot of ways to break up 1. And we need to have one of these be plus and one of these be minus, because we want to end up with a negative 1. Now, which one should be the minus and which one should be the plus? Well, we probably want 3x subtract 2x. So I think this will do it. Now, if you don't like this process, you don't have to do this. You can always pull out quadratic formula, and that's great. There's no judgments here. Does this work, by the way? 6x squared, that's good, plus 3x minus 2x is x, and minus 1. All right, so we're close. What do we conclude? Two possibilities. X equals 1/3, or x equals negative 1/2, because we have two things multiplying to get 0. And that's a good thing. When two things multiply and get 0, well, that says one of them had to be 0. And that's how we end up saying, well, either 1/3 or negative 1/2. Now, those are not points, but they're kind of close. How do we get to points? Well, we remember y is a half x. So we say, okay, our critical points, we'll have two of them. We'll have 1/3, comma, a half times a third, 1/6. And then we'll have minus a half, comma, minus a half times a half, minus 1/4. All right, so we've done the find. Now to classify. Now how do we classify? Well, for classifying, we do what's known as the second partials test. So we're doing second partials. Cool. Now the way that this works is we're going to do the following. We're going to look at f xx f yy minus f xy squared. There's a couple of possibilities. If this is less than 0, that equals a saddle. If it's greater than 0, well, then you have a max or a min, and what you do is you look in one of the slices and you say, okay, if fxx is positive, min, if xxx is negative, max. If this expression is equal to 0, we throw our hands up and say, second partials test is inconclusive. And but that's okay. Okay, so what do we need? Well, we need more derivatives. So we didn't write it down, but this was fx, and this was fy. So let's start getting to work here. Fxx times fyy minus fxy squared is equal to, taking the derivative here, derivative with respect to x, 6x. Coming to this one, taking the derivative with respect to y, -2. Subtract. Now, come here, take the derivative of the first expression with respect to y, or come here, take this expression with respect to x. In both cases, we get 1. Okay, so we see right underneath, here's fxx, here's fyy, here's fxy. Now, what next? Well, we plug in. All right, so here we go. At 1/3, 1/6, we have that this expression, and oftentimes this is called the discriminant, so we'll call it D. This is 6 times 1/3 times -2 and subtract 1. Well, 6 times 1/3 is 2 times -2 makes -4, subtract 1 makes -5. This is negative. Saddle. All right, good. That's our point. Okay, and then if we plug in -1/2 minus 1/4, well, what happens? We get 6 times -1/2 times -2, subtract 1. Now 6 times -1/2 is -3. -3 times -2 is +6. Subtract 1 is still positive, so that's greater than 0. All right, well, what are we in? Well, we're in either the max or min. We can look at either fxx or fyy. When we see negative values, right, -3 or -2, when we see negative values, that tells us we're max. And so, if we, well, let's just write our answer in all together so that they're happy with us, right? So 1/3, 1/6 is a saddle, and -1/2 minus 1/4 is a local max. Now, oftentimes we may not emphasize the max, may not emphasize the local, but it's good to include it. So there we go. Number 4. We're given z as f of xy is defined by z cubed minus xy plus yz plus y cubed equals 2. And we're asked to find, and they here use the symbol delta, and I'm more used to the partials. I'm partial to partials. Partial z, partial y at the point 1, 1, 1. So what that means is when x equals 1, y equals 1, and z equals 1. All right, well, how do we proceed? Now, there's a couple of ways to do this. One way is you can remember a big formula, and the other way is you can say, you know what, we're going to put on our thinking cap and have an idea. So we look at this and say, we say, well, we know that z is really a function of x and y. Now you might say, well, how did we know that? Well, it tells us right here. Boop. Z is a function of x and y. So an idea comes to us. And our idea is to say, well, since z is a function of x and y, let's take the derivative with respect to y. So we're going to think here of x and y as our variables. We'll call them our independent variables, which means they're free choices, but z depends on x and y. So x doesn't depend on y. So we're taking the derivative with respect to x, with respect to y, and just keep in mind x is a constant. Okay, so here we go. Now, before I do the next step, I'm going to write something down. The next part I write down we usually have in our head, but just to help as we're doing it, we can say, well, this is z of xy cubed, because I'm thinking of z as a function of x and y, minus xy plus y z of xy plus y cubed equals 2. And I just want to emphasize that z does depend on y. So when we take the derivative with respect to y, we have to account for z. All right. Well, let's start. Taking the derivative with respect to y of everything. So here, well, I see a y. Okay, so we got to account for that term. Chain rule. We bring the 3 down. Then we have the side part stays the same, which is z, and squared. But now take the derivative of the inside. The derivative of the inside is z. Well, what's the derivative of z with respect to y? The answer is it's the derivative of z with respect to y. Yeah, that's it. Minus xy. Well, x we're treating like a constant. So here we say, okay, derivative of minus xy with respect to y is minus x. On this term, we're going to have product rule, because y and z both depends on y. So, okay, the derivative of the first would be 1 times the second. That's z. Plus the first, y, times the derivative of the second. And the derivative of z with respect to y is still the derivative of z with respect to y. All right, derivative of y cubed with respect to y, 3y squared. And remember, we said we're taking the derivative of everything, including the other side, equals 0. Now, we could solve for derivative of z with respect to y, but notice we're going to plug in. So we can either solve for it now and plug in after, or we can plug in and solve. My advice is, if you know you're plugging in, plug in first, because it's easier to move numbers around than it is to move expressions around. So x, y, and z are all going to be 1, because we're at the point 1, 1, 1. What do we have? Well, we have 3 partial z partial y minus 1 plus 1 plus partial z partial y plus 3 equals 0. So here we plug in 1, 1, 1. And okay, well, that cancels there. We can move that 3 across and put those two together. So 4 partial z partial y is negative 3. Divide by 4, partial z partial y, which is derivative of z with respect to y at the point 1, 1, 1, is negative 3 over 4, and we're done. That's the answer. Good, good. Now you might say, wait, you said there were other things you could do. Well, there's rules. For example, if you think of this as f of x, y, z, if you take the right partial derivatives and divide, you'll get the right answer. But that requires you memorizing stuff, and that's dangerous. You know, you're young. I'm old. My mind has run out of space, and so I like to memorize ideas and processes. And so here I think it's easier just to say, oh, I want to take the derivative with respect to y. What depends on y and what doesn't? In this case, z depends on y. X is a free choice. Say, great. Take that derivative, simplify. Life is good. Number 5. Find all points on the surface given by x cubed plus 3x squared y plus 6yz minus 3z squared equals 7, where the tangent plane has an equation of the form ax plus ay equals b for some constants a and b. Now, what are we doing here? We should always think about what's our goal. Well, we see a couple of things. We see tangent plane. Say, okay, we're after tangent plane. And what kind of tangent plane are we going to do? Well, there's sort of 2 cases, namely where we have z is a nice function of x and y, or when it's all mixed up. We're in the mixed up case. We say, oh, cool. So since we're after a tangent plane, that says we're going to be using the gradient to find the tangent plane. So our idea is we say, well, look, if we have f of x, y, z equal to some constant c, then what we know is that the gradient of f at x, y, z, this right here, this is the normal vector of our tangent plane. So you say, okay, so that's what we're going to need to study. What does the normal vector look like? So let's take our gradient and take a look and see what we need. So we have the following. You say, okay, our f of x, y, z, we'll go ahead and just copy it down, is x cubed plus 3x squared y plus 6yz, subtract 3z squared. All right, so the gradient of f at x, y, z. Okay, so this is a vector. We're going to take three partial derivatives, one for each variable. We start with the x, because we just go x, y, z. So, derivative, that will be 3x squared, 6xy. There's no x, no x. So that's done. So, as a reminder, I'm just going to put some notes here. Partial f, partial z. Go to the next thing. Derivative with respect to y. No y. 3x squared, 6z, and there's no y. Okay, good. So this is partial f, partial y. Last part. Okay. Derivative with respect to z. Nope, nope. 6y, because y is constant, and minus 6z. All right, so there is our partial f, partial z. Now, what do we know? We're after a very particular form for our tangent plane. And the normal vector comes from our gradient. Look at what's the normal vector here. The normal vector, well, the coefficient of x is a, coefficient of y is a, coefficient of z is 0. So what does that say? It says that these two pieces have to be equal, and this part has to equal 0, right? Because we need the third coordinate to equal 0, and the first two coordinates have to match. All right. Well, So let's see what we have. We now set the parts equal. We get 3x squared plus 6xy is equal to 3x squared plus 6z. And 6y minus 6z equals 0. Now, this last equation, that's pretty quick. You move the 6z across, you divide by 6. We say, hey, that tells us y has to equal z. This first equation, those cancel out. We can even cancel out some 6's. And we say, well, what does that tell us? It says that x, y has to equal z. But we know that y equals z. Okay, so, all right, x, y equals y. Now, what do you want to do? You kind of are tempted to divide by y. Why are we not going to do that? Because if we divide by y, we might be dividing by 0. So don't divide unless you're 100% sure it's not ever going to be 0. Okay, so, so what do you do instead? Subtract the y across, and so we get y times x minus 1 equals 0. Okay, so this leads us to two possibilities. Either y is equal to 0 or x is equal to 1. Now we've got to start exploring these possibilities. So let's see what has to be true. Well, let's start with the y is equal to 0. Okay, if y is equal to 0, we know y equals z, so that says that z is also equal to 0. So we come up here, we say, all right, y and z are both 0. So we get x cubed plus 0 plus 0 minus 0 equals 7. Well, all right, that says x has to be the cubed root of 7. So the point that we're after, the only solution would be cubed root of 7, 0, 0. All right, now that's the only solution for the case y equals 0. But all right, we found a point. Cool. And what about our other case? Well, for our other case, we say, okay, we know x equals 1, and we also know that y equals z. So let's come up here. So x equals 1, so we're going to get 1 plus 3y plus, here we can think of it as 6y squared, because I can say y equals z, so I can replace z by y, minus 3y squared equals 7. All right, so, oh, we're running out of space, but that's okay, we'll make it. I believe in us. This is the same as 3y squared combined plus 3y, and then subtract 7 minus 6 equals 0. Everything has a factor of 3. Y squared plus y minus 2 equals 0. I think we can factor this one. Let's see. It would be y plus 2 times y minus 1. And does it work? Y squared, that's good. Minus 2y, minus y plus 2y, yes, plus y minus 2, which says, oh, y equals negative 2 or positive 1. So that actually gives us two possibilities. So namely, we have 1 for x, then y could be negative 2, or 1 for x, and then y could be 1 and c could be 1. And so we end up with a grand total of 3 points. Cubed root of 7, 0, 0, 1, negative 2, and 1, 1, 1. Now, let's make sure we answered the question. It asked us to find the points, and we did. It doesn't ask us to find the actual tangent planes. It only says the tangent planes has a certain form, and it doesn't say we have to find what they are. So it's always good to double check, make sure we answered what was asked. Because sometimes when you start doing a problem, you get so, amazed or dazzled. You get in the zone and you kind of forget, wait, what was I trying to do? It doesn't hurt to, when you think you've reached the end, go back and say, wait, did I actually answer what was asked? And if you haven't, make sure you do. So, all right. Oh, we're doing great. Let's keep going. Number 6. Find all absolute maxima and minima of the function f of xy equals x squared plus 2y squared minus 2x on the closed bounded region given by x squared plus y squared less than or equal to 4. For each extreme value, give the value of the function and the points for which it is attained. All right. Now, absolute max and min. Cool. So it tells us what kind of problem we're doing. So that's good to know. Now, what is an absolute max and min problem? I like to call it the making a list type problem. Remember, we're making a list and checking it twice. Can I find out which points are nice with absolute max and min to be found? Now, what's the game plan? Well, let's think about, before we get too far in our game plan, our region. So I'm going to do a quick sketch. Our region, that's given by this piece right here, the x squared plus y squared less than or equal to 4. That's a circle of radius 2. So we have our circle here. And the equals 4 would be just the outer edge of the circle. The less than or equal 4 says it's the filled in circle. So we say, all right, so filling this in. There we go. There's our region. Now, the make a list says, okay, where do we have the potential max and mins? You essentially say, look for critical points on the inside and look on the boundary. So let's start with the inside. So for the inside, we're going to look and say fx equals 0, fy equals 0, and solve for points. Well, take the derivative of the function with respect to x. You would have 2x, the derivative of that is 0, and then minus 2 equals 0. And then take the derivative with respect to y, 0, 4y, and 0 equals 0. Well, that's pretty good. 4y equals 0, we can solve for that. Y equals 0. Here, add 2 to both sides, divide by 2. That says x equals 1. Now, this tells us there's one point where both the partial derivatives vanish. Does it make our list? Well, that's a good question. So to answer that, we say, well, where does it fall? It's x equals 1, y equals 0, which would be here. That's in our region. If it had been outside of our region, forget it. Not important. But in our region, it makes the list. So we add it to our list. All right. So next up, well, we got to do the boundary. Now here, the boundary is not pieces, line segments, it's the circle. So how do we do our boundary? Well, we say, what's true? Well, on the boundary, it's x squared plus y squared equals 4. Now, the goal when you're working on the boundary is you say, I don't want a function of 2 variables. I want a function with 1 variable. 1 variable to rule them all. So, can we rewrite our function in terms of 1 variable, knowing that x squared plus y squared equals 4? Well, notice there's only one place y shows up, and it's as y squared. So we are like, ideal. Okay, we could say y squared is 4 minus x squared. So on the boundary, we really have, oh, our function looks like it's x squared plus 2 times 4 minus x squared minus 2x. Well, okay, x squared minus 2x squared, that's minus x squared. Then we have minus 2x, and then we have plus 8. So distributing the 2 across and rearranging. Now, once you can get down to one variable, we're good to go. We say, hey, let's just do it like we would if we were in a Calc 1 class. Okay, so we're looking for the critical points. Okay, so here I'm going to think of this as a function of x on the boundary. So what's the derivative? Well, minus 2x and minus 2 equals 0. And we solve. So that would lead us to x equals negative 1. All right, so what does that correspond to? Well, that says y squared is equal to, I'm getting too close to my list. Y squared is equal to 3. So y equals plus or minus square root of 3. So that's these points. So we have minus 1 root 3, and we have minus 1 minus root 3. Are there any other points to include? And the answer is yes. And here's the point where there's some subtlety. Okay, so be careful here. What's our subtlety? Well, notice that this function only makes sense for our region. That's all we care about. Where is this region going between? it doesn't extend everywhere. It only goes from -2 to 2. So here, this is 4 minus 2 less than or equal to x less than or equal to +2, which means that you have endpoints, and endpoints always make the list. They're like corners. Corners make the list. When in doubt, be careful and add things to your list. It's better to have too many points to check than to have too few and miss something. So we're going to also include our points -2, 0, and 2, 0. All right. Well, that's a lot for us to check, but we've made our list. What comes next? Well, what comes next is we plug in. Okay, so here we go. When we plug in 1, 0, so x equals 1, y equals 0, we'll get 1 plus 0 minus 2. 1 plus 0 minus 2 is -1. All right, great. Now, for the rest of the points, we're on the boundary. So what we can do is we can actually use the function on the boundary, which is a function only of x. So that'll help simplify some things. So, for instance, when we plug in -1 root 3 or -1 minus root 3, the x's agree. So let's see, we'll have -1 squared, which is a +1, times a -1, so that's -1. -2 times -1 is a +2, so -1 plus 2 is 1, plus 8 makes 9. And these will be the same. All right, good. Now, what about -2, 0? Well, we'll have -4, +4, and +8. So this is 8. +2, 0, we'll have -4, -4, plus 8, which altogether makes 0. Okay, so we've made our list. We made sure we didn't forget anything, so we checked, we got the interior, we got the boundary, made sure we didn't have any corners we didn't forget. All right, we now plugged everything into our list, and we're ready to give our answer. Let's double check the question. It says, find max and min, give the value and the points. So let's talk max. We scan our list. What's the largest number we see? 9. So that says, okay, absolute max is equal to 9, and the points, there's 2 of them. So at -1 square root of 3 and -1 minus square root of 3. Okay. Scan for the smallest number on your list, -1. So the absolute min is -1 at 1, 0. Only one place this time. And we're done. So we finished. Again, procedure, make a list, plug it in, look for largest and smallest values. Not too bad. Just be careful and make sure you do the boundary. The boundary is usually the hard part. The interior, not bad at all. Well, that's 6 problems down. That means there's still 1 more to go. Number 7, our final problem. Find the points, so there might be plural, on the curve given by x squared minus xy plus y squared equals 3, which are closest to the origin. And it says, use the method of Lagrange multipliers. Okay, so what method should we use? Yeah, Lagrange multipliers. Okay. Now, it's not so clear, but this turns out to be an ellipse that's been tilted a little bit. It's not easy to figure out which way it's tilted, but that's not important. We don't need to know that. What do we need to know? Well, we have our constraint, right? Because we have to be on the curve. So this is our constraint. And remember, what is Lagrange multipliers? It's really about optimization with constraint. Okay. So if that's our constraint, what are we optimizing? Well, okay, a good word to look for is one which ends in est, close est. So an est is an indicator of like you're trying to optimize that particular aspect. In this case, we're trying to optimize how close we are. So this is about distance. Now, if I think about the distance to the origin, if I'm at a point x, y, well, the distance here, that's this square root of x squared plus y squared. And at this point, we're like, do we have to deal with the square root? No, we don't. Because if I want to optimize this, I say, oh, I just need to make the inside small. Okay, so here's our goal. We're going to optimize our function f of xy, which is the inside, x squared plus y squared. So if you're trying to optimize an expression with the square root, and it's the square root of something, and there's nothing else, you say, oh, I just need to optimize the something. Constrained, or given that, g of xy, which is x squared minus xy plus y squared equals 3. In some sense, this was one of the harder parts of this problem. Even though we haven't gone very far, it's making sure we have a good start, the right setup. So, what comes next? Well, we have one relationship between x and y. That comes from our constraint. We're going to find another relationship for x and y, and that comes from the gradients. So Lagrange multipliers comes from saying that the gradient of f is a multiple of the gradient of g. In particular, this lambda is the Lagrange multiplier. That's what we mean. That's where that comes from. Okay, cool. So what does that mean? Well, we want f sub x is lambda g sub x, and f sub y is lambda g sub y. All right, so taking our derivatives, f sub x, 2x equals lambda g sub x. Well, that's 2x minus y. And then f sub y, 2y equals lambda g sub y. Well, that would be minus x plus 2y. All right, now, we don't really care about lambda. That's not important to us. We care about relationships between x and y. That is important to us because that'll help us solve for x and y. So our goal is get rid of lambda. And this comes into a strategy which I think is very useful. It's called solve for lambda. So we say, all right, well, solving for lambda, we get 2x over 2x minus y is equal to 2y over minus x plus 2y. And both of these are lambda. Now you might say, whoa, Steve, hold on, slow down. Won't that get you into trouble? Aren't you like shouldn't you panic about divide by 0 guy? But you'll be okay. Because what's going to happen at the next step says, oh, actually, you don't have to worry about divide by 0. After you've solved for lambda, you cross multiply. And then everything can be justified. So don't worry about that. Just solve for lambda, full speed ahead. All right, what do we get? Well, I'm leaving myself an awful lot of space here, aren't I? I should go use that. But we have 2x times minus x plus 2y is 2y times 2x minus y. And so that's minus 2x squared plus 4xy equals 4xy minus 2y squared. Oh, well, this is kind of convenient because we see that the 4xy's cancel. We can divide out by the minus 2's. And we're left with x squared equals y squared, which says either x equals y or x equals minus y. All right, so here we go. Let's explore. We have a couple of things going on here. We now know that we always have the constraint x squared minus xy plus y squared equals 3. And we have two possibilities. So let's do x equals y. Well, if we do x equals y, then this becomes x squared minus x squared plus x squared equals 3. Or x squared equals 3, which tells us that x is equal to plus or minus square root of 3. All right, that gives us, since y equals x, that gives us points, namely square root of 3, square root of 3, minus square root of 3, minus square root of 3. Okay, now that's one possibility. Other possibility, x squared minus xy plus y squared is equal to 3, and x is negative y. Okay? Well, this will become x squared, since negative y equals x, plus x squared equals 3. That's 3x squared. So this tells us that x squared equals 1, so x equals plus or minus 1, which gets us to the points 1 comma minus 1, or minus 1 comma plus 1. And we've now accounted for all possibilities. So when we have optimized on this curve, we ended up with 4 candidate points. But which one's closest? Well, we're trying to make the function f as small as possible. When we plug in root 3, we'll get 3 plus 3, 6. Here we'll get 3 plus 3, 6. Here we'll get 1 plus 1, 2. 1 plus 1, 2. So the closest ones are the ones which are smallest. So we'll just make some notes here. Here our distance, we can say our function is f. We'll put distance in quotes. F is 6. Here our distance, what we're trying to optimize, our f is 2. So this pair of points, these are the ones which minimize our function on the curve. Now, let's make sure we know what we're after. We were after find the points. So we're looking for the points, not the distance. So technically the distance is the square root of 2, not 2. But that's because we said, well, let's start by squaring. So our final answer is just those points. 1, negative 1, negative 1, 1. And we got our answer. Nice! We made it to the end! Woohoo! Good job, us! Well, I hope you enjoy this test. I hope that you enjoy the test you're going to take even more. Good luck. I believe in you. You can do it. Bye.